In this lecture, we'll be discussing antenna parameters. Antenna. Antenna is a metallic conductor system capable of radiating and capturing electromagnetic energy. It is used to interface transmission lines to the atmosphere and the atmosphere to the transmission line. It is a reciprocal device. Therefore, they may have the same characteristics when used to transmit and receive electromagnetic waves. The size of an antenna is inversely proportional to its frequency. Every antenna has directional characteristics and radiate more energy in certain directions relative to other directions. These are the antenna properties that we'll be discussing in this lecture. The radiation pattern is a polar diagram representing field strengths or power intensities at various angular positions relative to an antenna. If you look at the image, the line bisecting the major lobe or pointing from the center of the antenna in the direction of the maximum radiation is called the line of shoot. Next, let's take a look at the radiation field. Radiation field can be classified into two kinds. First is the near field or induction field. This refers to the field pattern that is close to the antenna. Next is the far field or radiation field. This refers to the field pattern that is of great distance. The power that reaches the far field continues to radiate outward and is never returned to the antenna. Next, we have radiation resistance. Radiation resistance is the AC antenna resistance that is equal to the ratio of the power radiated by the antenna to the square of the current at its feed point. It is also the resistance that, if it replaced the antenna, would dissipate exactly the same amount of power that the antenna radiates. Antenna efficiency. Antenna efficiency is the ratio of the power radiated by the antenna to the sum of the power radiated and the power dissipated. So in formula, we have efficiency is equal to P rad, or the radiated power, divided by the radiated power, P rad, plus PD. PD is the dissipated power. For the antenna gain, we have two kinds of gain. First is the directive gain. Directive gain is the ratio of the power density radiated in a particular direction to the power density radiated to the same point by a reference antenna. So by formula, we have D is equal to P over P ref, wherein D is the directive gain, P is the power density radiated by the antenna, divided by the power density radiated by the reference antenna. And then, power gain. This is the same as the directive gain, except the total power fed to the antenna is taken into consideration. So, we're gonna have to use the antenna efficiency in our formula. And here's the formula. A sub P, this is the power gain, is equal to D, the directive gain, times the efficiency. Now, note, if an antenna is lossless, it radiates 100% of the input power and the power gain is equal to the directive gain. Directivity. Directivity is a measure of how much power, power density, or power intensity is concentrated in a certain beam. This is the maximum directive gain. The antenna does not actually amplify the input power, it simply concentrates its radiated power to a particular direction. Next, we have the effective isotropic radiated power, or EIRP for short. This is defined as the equivalent transmit power and is expressed mathematically as these formulas below. First, we have EIRP equals the input power times the antenna gain. When you use this formula, your final answer will be in watts. We can also compute EIRP in terms of dBm by using the formula 10 times the logarithm of input power times antenna gain divided by 0.001, of course. We can also compute in terms of dBW. So in this case, we'll just remove 0.001 in the denominator. And the formula is 10 times the logarithm of input power times the antenna gain. The second kind of formula for EIRP, we have P rad, or the radiated power, times the directive gain, D sub D. This will yield an answer in terms of watts. Next, for dBm, we have 10 times the logarithm of P rad divided by 0.001 plus 10 times the logarithm of dt. Next, for dB watt, we have 10 log of P rad times dt. Notice the difference between these two formulas. First, for the power, in the first formula we have P sub in the second formula we have P rad. Meaning that in the second formula we just taken into consideration the efficiency. So P in times efficiency is just P rad. And now the second term is antenna gain and directive gain. So for antenna gain, we just also taken into consideration the efficiency of the antenna. Therefore, using any of these two formulas, we can arrive at the same exact correct answer. Next, antenna capture area and captured power. The antenna capture area is the effective area of the antenna, and it is a parameter for describing the reception properties of an antenna. Captured power is the power available at the antenna's output terminals. Its unit is in watts. And lastly, captured power is directly proportional to the power density and the effective capture area of the antenna. The captured power can be delivered to a load, such as a transmission line or a receiver's input circuitry. First, we have the power density, which is the power density at a certain distance from a transmitting antenna. We have this formula for power density. P sub D is equal to P sub N times A sub D divided by 4 pi R squared. In this case, P sub N is the input power of the antenna, A sub D is the antenna gain, and then of course 4 times pi. R is the distance from the antenna to the point at which we are taking the power density. And then the formula over here, A sub C is the effective capture area of the antenna, and it is equivalent to A sub R. This is also the antenna gain. The subscript R just means that the antenna is receiving electromagnetic signals, times lambda squared. This is the wavelength of the antenna divided by 4 pi. Now, the table to our right, we have antenna type and unitless gain. These are common antenna types in which the gains are given. So first we have isotropic. Isotropic antenna radiates in all directions equally. Therefore, it has no gain, since it does not direct the electromagnetic wave at a certain direction. So gain is just 1 Hertzian. We have 1.5 for Hertz antenna. We have 1.64, and lastly for turnstile we have 1.15. Now again, these gains are unitless. Next we have antenna polarization. Antenna polarization refers to the orientation of the electric field radiated from it. So under antenna polarization, we have three major categories. First, we have the linear polarization. Linear polarization may either be horizontal or vertical, depending on the orientation of our antenna. Next, we have the elliptical polarization, and lastly, the circular polarization. For the circular, we either have right hand or left hand circular polarization. And then next, bandwidth. I'm sure you've heard of this term before. For antenna, bandwidth is vaguely defined as the frequency range over which the antenna operation is satisfactory. It is taken as the difference between the half-power frequencies and is often expressed as a percentage of the antenna's optimum frequency operation. So remember the half-power frequencies, this is the -3 decibel bandwidth. Next, beam width. Beam width is the angular separation between two half-power points on the major lobe of the antenna's plane radiation pattern. Antenna beam width is sometimes called the -3 decibel beam width or half-power beam width. Antenna gain is inversely proportional to beam width. Now let's take a look at the illustrations below. On our left side, we have two half-power frequencies or half-power points. This is the -3 decibel points. So we just drew a line from the antenna towards those points. And then we measure the angle between those lines. And as it happens, in this case, it's 44 degrees. So the beam width is 44 degrees. On the right side, we just do the same. As you can see, there is a measurement, the -3 decibel power. This is the half power of the antenna. So again, we'll just measure the angle in between those lines. And then, of course, antenna gain is inversely proportional to beam width. The wider the beam width, the less directive the antenna will be. And the smaller the beam width, the more directive the antenna is.